All right, for number one, what do we get for the slope?
3.
Slope is 3. So we have a disagreement, is what we call that.
Oh, no, it's not.
All right, so
Oh, shoot.
is it a simple rise over run? Maybe. Well, the scalars are the same for the x and y axis.
It's 7/2.
7/2 is what we're saying?
Yeah.
So if you could get it. Now, if the scales are different, you may want to go by points. But in this case, the scales are the same, so you're fine. 1, 2, 3, 4, 5, 6, 7 up, 2 over. So the slope is 7/2. The y-intercept? 6. All right, now for the other piece, slope? 0, because it's a horizontal line. Y-intercept?
-4.
-4. All right, so for the first equation, I would say my equation, or first line, sorry, I would say my equation is 7/2 x plus 6. And for the second one, I would say y equals 0x minus 4, but I'm not writing 0x, so y equals -4. All right, so now it's just a matter of putting it all together into one equation. So f of x would be equal to, open your squigglies, we have 7/2 x plus 6 if x, what about x?
Is greater than 0.
Greater than -4, greater than or equal to, but less than. So it starts here and ends here, right?
Wait, do you have to write -4? Like, is less than equal to x, or you can flip it around?
You should have it lower value to higher value. Alright, so it's going from -4 to 0, right? Because the lowest x value for which the graph starts is -4. The highest x value where the graph actually ends is at 0. But does it ever get to 0? So does it ever get to 0? No, because it's an open circle. So what do I use? Less than or equal? Less than symbol, so less than 0. All right. The other piece is just a -4. All right, because again, we don't write the y equals. And if you write the y equals, it's incorrect. All right, you lose credit. It's not in the proper form. I know it's annoying. You don't think you should lose credit for that. And, part of me agrees with you, but that's what's going to happen. All right? Because you're basically saying y equals y equals. It's extraneous. All right. So where does my second piece start and stop? 0 and 6. All right. So it's going from 0 to 6 with all values of x in between, inclusive. Am I going to include the 0 and the 6?
Yeah.
So I'm going to use a less than or equal in both cases. All right. If you follow that procedure, you'll get it right every time. All right. Write the equation of each part. Work from left to right on your graph. Always from left to right. All right. If you keep that in mind, everything's going to work out. All right. So in the second graph, we have the same y-intercept. That's fine, but the slope here is what? 1/2. So m is equal to 1/2. We're saying it's 1. So we're going up 2 and over 4 units. So the slope is 1/2. Yeah. The y-intercept is 6. So the equation is y equals 1/2 x plus 6. If the scale throws you for a loop, do it by coordinates. And what I mean by that is, you know the slope formula, change in y over change in x. The coordinates, -4, 4, and 0, 6. Use change in y over change in x to account for that, and then you'll have your slope. All right. The other piece, slope is what? 0, y-intercept? -5, so I would say y equals what? -5, because 0x minus 5. All right, so I'm going to write my piecewise function, f of x equals, we have the 1/2 x plus 6, if, where does it start, where does it stop in terms of x only? -4, then it goes to the 0. All right, so those are the two relevant values. So -4, does it include the -4?
Yeah.
Yes. Does it include the 0?
No.
No, there's an open circle there, so less than 0. The other piece, -5, if, where does it start, where does it stop?
-4. Oh wait, no.
7, 0.
0 and 7, all right? Those are our two relevant values, all right? Draw a little dashed line to show you. All right, so we're starting at 0, stopping at 7, including both?
Yeah.
Yeah, so less than or equal in both cases. All right, there really is no, I mean, I don't want to say there's no cutting corners, but there's minimal cutting corners here. You know, you have to take into account all these little details. If you don't, you're missing something. And if you're missing something, it's going to be wrong. All right. And as you know, the penalty for missing something is more severe when it comes to a multiple choice question, because you miss a little something, you choose the wrong choice, and you lose full credit. Free response, different story. Maybe you only lose half a point or a point, but those little details, they make all the difference. So if you're one of those folks who seems to understand stuff and then gets annihilated on the multiple choice questions when you take a test, I'm talking to you. All right, so you got to pay attention to those little details. All right, so we're going to learn about word problems. Well, every unit has them, right?
Oh, goody.
All fun and games until you do the word problem.
Everybody gangster, so the word problems show up.
The reality is that we just need to somehow come up with a piecewise graph from the word problem that's given. So in the context of the problem, there's going to be enough information for us to make a determination of, you know, what that we need in terms of the piecewise. So let's just read through it and see what we got. Mateo's walking to school. It's a nice morning. Okay. So he's moving at a comfortable pace. Oh, that's why they told us it was a nice morning. Because otherwise he might not have been moving at a comfortable pace. It's a terrible morning, so he's moving at an uncomfortable pace. None of that is necessary. After walking for 9 minutes, he's 6 blocks from home. So they're addressing why he's walking so slowly. He stopped to answer a text on his phone from his mother, right, probably in the middle of the street. That's what people do. After 5 minutes standing still in the middle of the street, of course, he walks home quickly in 6 minutes to get a paper he forgot for school. Somehow it's 5 minutes of texting needed to cover all that. Model Mateo's distance from home D in blocks as a function of time, T, in minutes since he left. All right. So, all right. Looks like we're doing it by points. After walking for 9 minutes, he is 6 blocks from home. All right, that should be easy enough. For 9 minutes, he's 6 blocks. At a point right there. After 5 minutes of standing still, he walks quickly in 6 minutes to get a paper he forgot for school. He walks home quickly in 6 minutes. All right, so he stood still for 5 minutes. So 1, 2, 3, 4, 5. And then for 6 minutes, he somehow that's quick, I guess. He walks home. So his distance from home should be 0. So he started off at a distance of 0. And he ends up at a distance of 0. And this whole process took 20 minutes. So he's definitely late for school. So we're going to connect these points with a linear, I painted myself into a corner there, lines, linear functions. Just clean this up. All right, so we have a graph. So it looks like a trapezoid, but that's irrelevant. How many blocks did Mateo travel before he turned back home? Well, they gave us that in the problem. You travel 6 blocks.
6 blocks.
Determine a formula for the distance he is from home D over the time interval 0 to 9. All right, so the distance he is from home D. Well,
6.
that sounds probably more intricate than it is, but really what it's asking for is write the equation of this line. All right, so what is the equation of this line? Well, I need some information. I need a slope and I need a y-intercept. All right, so we can do rise over run. Now you could do it by points, like I said, or you could do it by just counting boxes. But again, you got to be careful about going by counting boxes, because sometimes the scale can be so funky that going by, just counting rise over run could be troublesome. But what we can do, and I'm going to do it at least this one time just so you have it on paper, is I'm going to do it by points, and then we'll verify it by actually just counting. So we have coordinates 0, 0, and 9, 6. We need a slope, which is change in y over change in x. So rise over run, 6 minus 0 over 9 minus 0. All right. So simplify that, you get 6/9, which reduces down to what?
2/3.
2/3. All right. So we have a y-intercept. What's my y-intercept?
0.
B equals 0. So my equation would be y equals 2 over 3 t plus 0, or we would just say y equals 2 over 3t. All right, and we can verify that with rise over run, just counting boxes. So you're going up 1, 2, 3, 4, 5, 6. You're going over 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so 6 over 9, you get your 2/3. All right, either way. But again, you got to be prepared, because the numbers could be funky. And then when we move into statistics, where the numbers definitely are funky, discussing decimals and all that sort of stuff, you're going to be dealing with cases where you have to do it by a formulaic approach rather than counting boxes. All right, so from 9 to 14, that one should be a little bit easier, because I know the slope is what?
0.
Slope is equal to 0. Now, it never gets to the y-axis, but if it could get to the y-axis, what would the y-intercept be? 6. So I'm looking at an equation, y equals 6. All right. And so for the last one, same idea, slope. You could do the rise over run. I'll do that. I'll do it just that way this time. So we're looking for, we're down 6, so negative 6, and then 1, 2, 3. All right, so our rise over run is negative 6 over 6, which should give me a what? Negative 1. So m is equal to negative 1. Now the y-intercept is a little bit of a different story here. All right, so you could just count back, but if you're really far away from the y-axis, that could be a problem. You may want to consider going with a different approach. All right, that different approach would be the point slope form. We did this way back when. So that's the beauty and the drawback at the same time of a Regents course, is that you're expected to know stuff that you did even back in September, October. All right, so no time like the present to review it. Y equals m times x minus x sub 1 plus y sub 1. This is the point slope form. All right, so all we need from this is a point that we know is on the graph and the slope. All right, so looking at just this part of the graph, just this piece, give me a point that you know is definitely on it.
20, 0.
20, 0. I like that one because it's nice and convenient. All right, so we have a point. I'll make a note, point 20, 20, 0. So we would say y equals -1 times x minus 20 plus 0. All right, in which case we would simplify that down to y equals -x plus 20. All right. Now, that technique is not always going to be necessary because sometimes you can actually just count back. You've done that, you did that in the homework, you did it in the classwork yesterday. And maybe you could even extrapolate here and say, all right, I'm just climbing the ladder, climbing the ladder, climbing the ladder. Where would that get me if I could go off the grid? You know, you could probably get at least close to a sense of what the answer would be. But if this, instead of being at 14, if it were at 74, you're not getting back to the x-axis or the y-axis that way. So that wouldn't make much sense. Oh, I used x again. Dang it. Should be y's. Sorry, t's. Yeah, because we're working with t instead of x in this case. All right, so tiny little adjustment. All right, so what we have to do here is write the piecewise function to represent this. And what that means is that I'm going to take the leftmost piece, write it in my piecewise, and then the next one as I go from left to right, and then continue on from there. The good news about a problem like this, and really, I mean, there's a wide variety of different ways they could ask you a piecewise, but most of them, there are a few exceptions, but most of them involve them giving you the domain in some way. And I found that the thing that people struggle with the most is determining the domain. Right? So I have f of x, sorry, in this case it'd be f of t, function of t, would be equal to, the first piece was 2/3 t, but that only happened if t was between 0 and 9. That was given. The second piece was y is equal to 6. That only happened if t was between 9 and 14. And then the last piece, -t plus 20. But that was only if t was between 14 and 20. All right, so that last part should be easy because you did all the work prior to that. All right, so the one little twist on this is part E, where you have to use a different approach. But you got to go back and review old stuff. I've been saying this repeatedly. I hold on to your packets for safekeeping because most students, when I asked them to bring their packets in the last couple weeks of school when we're reviewing hardcore for the Regents, they're like, oh, I don't have packet 2, I don't have packet 4. I'm like, oh, okay, so what am I supposed to do, print up all these copies for everyone? That's not going to fly, and even if I did, they'd be all blank. So I hold on to them, but you're welcome to take them back at any point if you think you need to review old stuff. Linear functions, that was a while ago, but this is something that this year was not the first time you saw it. So when you're grumbling and saying, I don't remember that, well, you should. Right? And so if you don't, go back and review it because it's that important. Right? It's not going away. Right? None of the stuff that you're learning this year is ever going away. Right? Maybe next year. Maybe there'll be some topics next year that'll go away. But this year, everything that you learn is going to come back repeatedly throughout the course of your mathematical careers. Some more than others. Factoring, linear equations, things like that. Those will come back more than some other things. But there are some hidden topics that we cover in this class that you're like, oh, I'm sure this will never come back, and then it comes back, and you're like, oh, I guess I was wrong about that, right? So you can't neglect your previous studies. All right. Number 2, a substantial snowstorm is hitting the northeast region and is predicted to snow at a rate of 2 inches per hour for the first 3 hours of the storm. The storm is supposed to pause for 3 hours and then resume at a rate of 1/2 inch per hour for the next 4 hours. The depth D of the storm is the total number of inches of snow that has fallen at a given time. Graph the snow depth as a function of time since the storm began for the length of the storm. All right, so we can kind of piece it together based on the information that they gave us. They're telling us, let me go highlighter here, a rate of 2 inches per hour for the first 3 hours. All right, so we'll do it by points. So we'll start it off. 2 inches per hour for the first 3 hours of the storm. So, time since the storm began. All right, well, if time is equal to 0, how many inches of snow are on the ground? 0. If we're going at 2 inches per hour, after 1 hour, how many inches of snow are on the ground? 2. After 2 hours? And after 3 hours? 6. All right. Now, from this, we have a lot of information. We know that the slope is equal to 2, and the y-intercept is equal to 0. All right. I'm just going to hang on to that information. The storm is supposed to pause for 3 hours. All right. That means that we're not gaining any more depth of snow. All right. So for 3 hours, the depth is going to remain the same. So 1, 2, 3. That gets us here. All right. Slope of 0. Y-intercept of 6. All right. Then resume at a rate of 1/2 inch per hour. All right. For the next 4 hours. All right. So resume at a, oh, that is not a highlighter. All right, so after 1 additional hour, where am I at? How many additional inches of snow have I gained? 1/2 an inch. All right, so after 2 hours, then that would be 1 inch, 1 more inch. Then I'm going a total of 4 hours. So another 1/2 inch and then another whole inch, right? What's the slope here? 1/2. All right. That rate of change that they're giving us in the word problem, that is the slope. A rate and a slope are the same thing. So when they say the rate of 2 inches per hour, they're telling you the slope. Rate of 1/2 inch per hour, they're telling you the slope. All right. That's all the information that we have. So that's pretty much it for the graph. The one thing I don't have here is the y-intercept, but this one I could dial back. I don't need to do it by points. Marie?
Yeah.
Yeah, it looks like 3. All right. All right, so we graphed it. How many hours is the snowstorm, or how many hours long is the snowstorm? 10 hours, right? How many total of inches of snow fell? 8. It's a snow day. All right, we need a piecewise function. So we have 3 lines that we could put together here. First one's easy enough. Now it's f of t, so it's an adjustment. What's my first? We'll worry about the domains all in one shot. But for now, what do we say about the black function here? What's the equation?
2t.
Just 2t. What about the red one?
6.
Just a 6. And the blue one?
1/2t plus 3.
1/2 t plus 3. And we'll take care of our ifs. So for the first 3 hours of the storm, we're at a rate of 2 inches per hour. So that's going from 0 to 3. All right, less than or equal, right? Because you could have 0 hours. Can you have 3 hours? Can it get to the third hour? For the first 3 hours, yeah, it implies that we're actually getting to that third hour. Storm is supposed to pause for 3 hours. All right, so after the third hour has stopped, then we're paused, right? Yeah, I think this is like perfect for a snow day because like it snows in the morning, then it pauses for a little while, then it picks up again, so all the buses will be impacted. But yeah, so it's after the third hour that it starts the pause happens. So we would say 3 is less than t, all right? Because we're not paused at the third hour because it said we're still at a rate of 2 inches per hour for the first 3 hours of the storm. So right at that third hour mark, it's still at that rate of 2 inches per hour. It's once you hit 3 and like 1 microsecond, that's when the last flake comes down, you know, so no more accumulation, right? And that's gonna pause for a total of 3 hours. So, but we will get to that third additional hour, so we're up to 6. All right, then we have 4 more hours after that, so 6 to 10. After the 6th hour is completed, the snow picks up again, but at a slower rate. And then it keeps going for a total of 4 more hours, but it is until that 10th hour that you will have some snowfall. All right, so you have to really consider what the problem is telling you, but you know, in a case like this, it's something that you can relate to. You see it every year. I mean, some of us watch the forecast a little bit more closely than others, but when you do, you realize that this makes sense. All right.